and I'll give you a bit of an overview. Okay, well, I mentioned to you earlier that it's semi-refrigerated. Semi-refrigerated, we can not fully refrigerate, we can hold the liquid in tanks at moderate pressures. Fully refrigerated LPG is when we get full reliquefaction going. We saw these pictures earlier, so I'll move on and look at the operations, tanker operations. Now, if a ship comes out from dry dock, what conditions it's in? It's empty. There's nothing in the tanks. It's in dry dock. So the first thing we have to do is inert it. The tanks are full of oxygen. Well, not oxygen, full of air, which contains 21% oxygen. So we can't put gas in there, so we inert the tanks. So we put nitrogen gas into inert the tank. And then we introduce some gas, some cargo gas, in order to purge the tank, cool it down. So as the liquid comes in and it's flashing off, it's drawing heat from the tank, cooling it down. And so we cool the tank down, we load it, we go on loaded passage, we get to the discharge port, discharge the cargo, and then we go on a ballast passage back maybe to the same place to get more cargo. If it's the same cargo, it's dead easy. We just go back and we reload again. So that's the cycle of the cargo. Okay, now if we want to take the vessel out of service again, we go back to the same condition where we go, should be another arrow here, we go liquid free, we inert, we now air it, we add fresh air, and to get it back to ambient conditions, we go back in for tank cleaning. Now on an oil tanker, for example, tank cleaning is essential because the tanks do get very dirty because of the nature of the crude oil that's being carried in it. But as you'll see from the inside of these gas carriers, the tanks are spotlessly clean. There should be no dirt, no residue, nothing left behind. So the tanks are very, very clean. So the cargo handling principles, look at principles, onboard equipment, oil or gas, treatment before commissioning, vessel operation, dry dock. Saw this earlier, oil or gas stated, and this is where we left our propulsion diagram. So cargo handling equipment is installed in the deck house on the vessel itself. These are the compressors for handling gas. We've got high duty compressors. This typical here, 15,000 to 35,000 cubic meters per hour. And during tank filling, if we're taking liquid into the tank, then the ullage space, or the space above the liquid, we need to return the gas to the shore for reprocessing, for re-liquefying, and because they have the facilities on board to do that. So we use these compressors to turn the vapour. During loading, we turn the cargo vapour generated by the gas displacement. Pipe compressor doesn't work correctly. So if the vapour can return back to shoreside, naturally, fine. If not, we would have pumped it back. And we also use the compressors during warming up. So we have low duty compressors, smaller capacity, and the task here is to control the boiler pressure. Sorry, I jumped on too far ahead there. Gas heaters, the boil off and warm up heaters. And we use boil off gas heating together with the LD compressor, and we use the tank warming up together with the HV compressor. We also use a vaporizer, which is used to force cargo, and we'll come to that in a second. Again. Jump too far ahead there, sorry. When we're using boil-off gas, the boil-off gas is a natural process caused by the input of ambient temperature into the gas that causes the boil-off. So we use boil-off back into the boiler, or as you've seen on the video earlier, into the diesel generator that can use gas. So there's two things we can do. We can use minimum gas, so we only use the boil-off. So how do we make up the rest of the propulsion fuel if we're using minimum boil-off? We have to use diesel oil, yeah? So depending on the charterer, depending who owns the cargo, depending how much is being delivered at the other end, and depending on the cost, will depend on how much gas we burn compared to how much diesel we burn. If we go on what we call mini fuel is minimum gas boil off. So whatever boils off, we pipe it back to the engine room and we burn it in the boiler, or we burn it in the engine. In order to maintain the vessel speed, we then have to burn diesel. Okay. Now we saw that it was 0.1 to 0.15% can boil off in a day. So if we've got a long distance to go between ports, let's say we're going from the Arabian Gulf to Japan, we want to get there as fast as possible so that we don't boil off a lot of cargo. If we want to deliver the maximum cargo to the customer, so it depends on the price we're going to get for our cargo. If, however, the LNG price is cheap compared to bunkers, we might either slow down so we don't get there so quickly, so we're going to burn some more boil off, or what we can do is go for maximum gas. And what we actually do then is we use a vaporizer and what we force the tank, so we force boil off. We make extra boil off gas. So we make extra boil off gas, so we burn more gas in the engine or in the boiler than we do fuel. So that's what we call forcing. So we use a vaporizer to force that. So we're actually encouraging, we're forcing boil off to happen to give us more gas as fuel. And so you're quite happy with that, yeah? So whether it's minimum or whether it's forcing, that's very much to do with the charter, it's to do with the cost of bunkers compared to the cost of, when I say bunkers, I'm talking about fuel oil bunkers, whether it's diesel or residual. It's going to be costly. So if we're in boil-off gas mode, that's conventional boil-off gas mode. We've got our LV compressor, our boil-off heater, boiler in the engine room, forcing vaporizer, mist separator, and so what's happening here now is boil off, going up through this mist separator, and so the gas, we don't mist separator, we don't want liquid going here, so we just gas only coming up here to the compressor. Bearing in mind this gas is cold, -762, this is chilled gas going up here, it goes into the boil-off heater. The boil-off heater heats the gas up to about 20 degrees centigrade or so, and before the gas gets piped back to the boiler. Now, the pipe work going back to the boiler, it's double skinned. So we've got the gas pipe in the middle, we've got another pipe on the outside. In the middle, in this annular space, we have gas leakage probes and alarms. So if our gas pipe's from a leak, it's not going to leak to the atmosphere, it will leak to it's between two pipes. So it's for safety, so it's double skinned pipe, and it's piped back to the boiler. And then that gas is always ignited and it's burned in the boiler. So if this gas can't supply enough, then the boiler is arranged with it has gas burners and it's a fuel burner in the middle. So we can just put more fuel in. So the boilers are very automated. We can set our steam pressure, we can set our steam temperature, we can set our shift speed. So the plant will modulate, it will make whatever we decide to do, whatever speed we get from the propeller, then that has to be provided from the engines or from the boilers, and then we can allow it to be controlled by supplying extra fuel to make up for what we're lacking in gas.
Okay, what about the mist? Goes back to the tank?
Yeah. So the balance required to drive is by bunker oil. So the propulsion now, if we require more, we do in this case, comes from the bunker oil. Gas only mode. If we use bunker only, natural oil isn't enough to drive the ship. There's just not enough gas there to give you the power. So we then use additional gas that is provided by forcing. So we take liquid from the tank, we heat it up so that it expands into gas, and that's what we call forcing vaporizers. So forcing more vapor. We're taking two streams here. We're taking gas from the top of the tank, which is maintaining the pressure at the correct level, and then we're taking liquid from the bottom of the tank and we put it to a heater, which causes it to flash from liquid into gas, and we put extra gas into the boiler. So additional gas provided by forcing. That's what we call forcing the cargo. So this would be burning just pure gas now. Gas only mode. So in terms of emissions, our emissions are going to be very good because there will be no sulfur products unlike you'd get in the fuel oil. But at the same time, we're using cargo. We're using up cargo. But if the cargo is cheaper than the bunkers, then it's cost effective. It just means we've got less cargo to get there. Yeah, there's the mist set there, drain back into the tank again. temperature wise, leaving the tank around about 100 minus 140 degrees centigrade. Coming out the force of vaporizer at minus 40. Going into the LV compressor. Remember, this is a much bigger quantity than we've got coming in here. Through the LV compressor, into the boiler heater, and then into the boiler again. Okay, any questions on that bit? You're quite happy with the trade-off between fuel and gas. Okay, before trial or after dry dock, we talked about this method earlier. We bring in nitrogen, an IG generator. Now, on a conventional steamship, what we use for IG is the exhaust from the boiler. The exhaust gas from the boiler, it contains very low oxygen. We keep the oxygen less than 5%, normally about 2% is the oxygen content of the gas leaving a boiler to stack. However, in the uptake of the boiler, we draw off the exhaust. The exhaust, which will contain nitrogen, it might contain some sulfur products, and some water vapor, H2O. But we put that gas through a scrubber, what we call a scrubbing tower, and it washes the gas. So what's coming out basically is effectively clean gas, nitrogen. But we don't want to do that with this plant, because in an oil tanker we're putting that into the ullage space above the cargo, between the cargo and the deck, tank top, and it's at ambient temperature, so it's fine. So if there's any moisture in that inert gas from the boiler, then it doesn't really create much of a problem. However, if there's any moisture coming into here, it's going to cause problems by freezing. So what we do is, instead of having uptake gas, which is cooled and scrubbed, we will have an inert gas generator providing us with nitrogen in effect to allow us to inert the tank. Obviously, if the tank is full of air to start with, we need to get rid of that air and we need to get the tank so that there's no volatile atmosphere in there that contains air and gas. Because otherwise, you see the size of these tanks. It's like an oil tanker. An oil tanker is actually more dangerous when the tank's empty. When the tank's full, it's got very little space at the top, and it's normally very rich. It's over-rich with vapour, so it's too rich to actually ignite. But when the tank's empty, if it's got vapour in it, and there's a small amount of air gets in, it can quite easily perform a flammable mixture, and then if that ignites, you can get a massive explosion. So this is really why we're inerting, and we're always inert before we introduce cargo into the tank. So that's my tank filled now with inert gas, and you'll have a purge line coming out, so that obviously if the inert gas goes in, air gets purged out. You can measure the atmosphere. We've got instruments to measure the atmosphere in the tank. So the purpose is to reduce the humidity of the air in the tanks, prevent crystal forming. So switching out gas to tank atmosphere 2 points minus 20. Okay, it could take up to 40 hours to dry and inert the tank fully. Seems like an awful long time. cargo tank gas filling. We want to introduce gas into the tank now. So purpose of this is to replace the inert gas and eliminate all the components in the inert gas. So we now bring gas into the inert atmosphere. So obviously we've taken the air away, any O2 that's in the tank, replaced it with inert gas. Now we're going to drive out the inert gas and replace it with actual cargo gas. So we go through the vaporizer and the gas enter the tank. Because it's at a much colder temperature, it starts to cool the tank temperature down. So we need to be connected up to the onshore facilities for doing this. And the purpose of this is to reduce the temperature in order to avoid excessive vaporization during loading, to limit the thermal stresses occurring in the components of the vessel itself, the tank. So everything's got to be done very gradually, very slowly, so we don't have thermal stresses occurring in the tank.
Do they use pumps to pump the cargo or only pressure?
No, they use compressors. Compressors, yeah. Rotary type of compressors. So because it's vapor, it's just compressors, rotary compressors that pump the gas back to a facility.
But in the concerning for the vapor that comes out of the gas, right? Okay.
Yeah. So this is cooling down now. So we're putting liquid gas into the tank, and as the liquid's going in the tank, what's it doing? It's expanding, it's flashing off. Its temperature wants to be low, so it's taking in heat from the surroundings, and the tank is starting to chill down. You know, like if you use a CO2 extinguisher, it gets frost when it expands from the high pressure liquid to the vapor. Then the same thing is happening here. This is cooling down, starting to cool the tank down. So this can take up to about 10 hours to achieve the cool down, and the tank temperature can be down -30. So all this is carefully monitored. We need to monitor the pressure in the tank as well as the temperature in the tank. So if we do this too quickly, you can overpressurize the tank. So it's done slowly. Okay, the amount of LNG used to cool down is proportional to the surface, the cubic meter of tank capacity. So you get 40,000 cubic meters, takes 12 hours, and it's going to consume 450 cubic meters of LNG. When we say consumed, it's not really consumed, is it? It's returned back to the shore, yeah. It's not like burnt in the boiler or anything, we're not really consuming it as such. 125,000 cubic meters, again it just uses more gas. So atmosphere change these are different types of tank, MoS Rosenberg and gas transport. the MoS Rosenberg is the spherical tanks, and these are the sort of honeycomb shaped tanks. So now we move on to loading itself. We want to start loading cargo into the tank. Now that we've cooled the tank temperature down, it's ready to accept the cargo. We start filling it up, and we've got vapor in this space here. Again, pressure in the tank has to be carefully controlled. So we use the high duty compressor, pump the vapor back to the shore facility. Yeah. So as this is coming in and this is going out, we have to make sure the pressure balance is there so that we don't overpressurize the tank. Now we're loaded. Got cargo in the tanks, and if we go back to the state we talked about earlier, it was natural boil off. So again, we're just allowing for natural. This yellow here signifies the insulation around the tank. The tanks are very heavily insulated. Even so, heat will still get through and boil off over time. So we're looking at continuous recovery of the boil off. Again, as we said earlier, that's going back to the boiler and burning the gas. Additional gas, what we're going to do, we're going to force it. So we put the forcing vaporizer on, and this is the fuel gas demand is greater than the actual boil off. We need the use of the forcing vaporizer to create additional vapor. So, in practice, all the boil off rates have been recorded. 40 to 50,000 cubic metre cube LNG carrier, loaded 0.23% per day. That's a relatively old ships, and unballast about 0.18% per day. Bigger vessels, 135,000 cubic metres, 0.15% in current ships, and it's envisaged that that rate would drop down to 0.08% per day on balance. Unloading. Now we've got our cargo to Japan or wherever we are. We're going to discharge it. So we're putting it to the onshore facility. It's going to take 10 hours operation, and then we're going to empty our tanks to the shore side. So again, maintaining the pressure in the tank, we do the opposite this time. So we take gas from the shore back into the tank to make up for the liquid we're taking out. The last thing we need to do, as well as causing overpressure, we don't want a vacuum in the tank. A vacuum will collapse the tank, cause major structural problems, because it's a big tank, it's large volume, so even a small amount of vacuum in there would cause the tank sides to come in, to start to crumple and implode. So that could damage it severely. So we need the gas to replace the liquid that's been removed and discharged to shore. Unloading. Abnormal operation. We're discharging cargo to shore facility, and we use a vaporizer complementing LNG vapor from shore, or no shore connection for gas replacement available. As I said earlier, vacuum, we don't want any vacuum filling in the tank. So we could create our own pressure if we didn't have, if we were only sending the gas, the liquid ashore I should say, and we didn't have a facility for coming back from shore, we could have our own onboard vaporizer, which is still taking some liquid from the tank and heating it up and putting it back in again as vapor, which is just maintaining tank pressure. But that's not, it says there that that's an abnormal operation, so that's not something we would be doing if we could help it.
Can we supply the tank with enough gas in order to maintain the pressure instead of using the
No. It needs to maintain the gas atmosphere until the cargo operation's finished.
without any mixer or
No mixing of anything else. Yeah, it needs to be 100% methane LNG in the tank stage. Temperature as possible. How do you assure temperature control? Well, we need to regulate the rate of the vaporization. So that's us discharged with cargo. We've now got more or less empty tanks, but we still have some. We've got ballast, but we need to have a volume of cargo retained on board. Keep the tanks cold, view the next loading. What do we mean by unpumpable?
When the tank is very cold, the last part of the pump you cannot touch it.
Yeah. So we can use the evaporated gas as fuel. So we carry, as I said earlier, it's sometimes called heel, the amount of cargo that's kept on board. We need to keep the cargo on board. If the next voyage isn't too far away, we're going to get to another loading port. Tanks are still to be kept chilled so that we can accept another cargo. Providing it's the same cargo process, the same gas.
What about the gas vapor? It's still being inside the tank also?
Yes. Yeah, you still got vapor in the tank here. So now, once again, we're taking vapor back, and we're going to just control the pressure in the tank. Back to the boiler. Keep the temperature of the tank correct for getting it back to the loading port. If we discharge the cargo and we don't need to load another cargo, suppose we were to go to repair yard or suppose we were to go to tie dock, then we need to get the tanks ready for that. So we let the tanks, we warm the tank up. So we use the hydraulic compressor to circulate the gas and the heaters to warm the gas up. Yeah. So the AC compressor circulates the gas, heaters warm it up, and the remaining LNG in the tank is vaporized. So taking it from 140 to 0 degrees centigrade, so that's it starting to warm up. Some hours later, we've got no liquid left. Warming up is finished when the tank reaches consistently throughout the tank. It's at 0 degrees centigrade. So again, this is averaging the temperatures here. We're taking it down to 0 here, it's 30 come out here, we heat it up, and we're warming the tank up now. So we've got the curves there warming up, flow rate and time, heat exchange, temperature. It's all done, as you can see, very slowly over a large number of hours. And then we're going to fill the tank with inert gas. Again, nitrogen generator. And it's operating in the dry air mode. Purpose is to allow access of personnel inside the tank to make inspection of performing work. It's not often you get a chance to go into these tanks, because normally the ship is in its working cycle. It's either loaded or on ballast passage is working. Around the tank, we've got insulation and we have air. We introduced air, oxygen content, O2, 21% is a normal O2 content by volume in air. So we allow air into the ullage space around the tank, just kept inerted. And then we go into dry dock. What's going to happen in dry dock? Maintenance, repairs. Dry docks are one of the biggest causes of fires, explosions that happen on board ships. Because what happens is if you get a ship, especially like oil tankers, where you have compartments that are supposedly gas-free, and they've even been certified gas-free, and then someone adjacent starts welding, then all of a sudden a spark or something, and then an explosion can happen. So we need to make sure that tanks are absolutely free of any cargo. We test for hydrocarbons, and we test for the atmosphere for make sure it's 21% oxygen. Because dry docking, we have a lot of people on board, there's a lot of stuff going on, and sometimes the contractors are not familiar with the ship or the ship systems, and the ship staff have to keep an eye and make sure that there's no dangerous situations arising. Particularly if someone's welding. If I'm welding on this bulkhead here, what's on the other side of the bulkhead? You know?
Captain. On the side? Or another side?
It could be another tank, yeah. I mean, if I'm a contractor, I might not be aware of what's on the other side. I might think it's just another room next door. It could be a fuel tank.
And
yeah. And I'm starting to weld on it. So if you're the ship staff and you know these things, you should be able to keep an eye, make sure that there's no dangerous practices. So after dry dock, we sort of do the same procedure. We take the ship back into service, and if we had any major works, we might do some trials and go back to sea, and then go back into service. So earlier we looked at the cycle where we loaded passage barrels past the same cargo, and then we load again. If we have a different cargo, then we have to make sure we're liquid free, gas up, purge again, there, then we start to get a bit complicated. But certainly before we get into dock, what we've always got to do is air the tank, get it back to atmospheric conditions, all cargo tanks. Okay, there's some other diagrams there showing more detailed systems, which I don't think we'll cover for the moment. But that was our basic operations that would be carried out on a LNG tanker. And that's cycled operations, LNG cycled operations. So for your first, I think that was your first sort of taste of LNG operation or something, isn't it? Yeah. Any questions?
Yeah. Thank you.
No, just you know, it's actually quite in the LNG operations have been going on for over 50 years, believe it or not. Starting off on a smaller scale and then moving up to these bigger vessels. And as such, there haven't been any great disasters concerning LNG. The obvious problem with LNG is what we call a loss of containment. Containment means keeping the liquefied gas in the tank. If it escapes, it increases by 600 times its volume. So the liquefied gas escaping from a tank, 1 cubic metre all of a sudden becomes 600 cubic metres. That's a lot of gas. And if that ignites, then it will cause major explosions. Now, the Japanese have been very conscious of this and being an importer of gas. A lot of LNG carriers over the years have travelled to various ports in Japan to just charge cargo, and they've been very very careful on the safety procedures, and touch wood, there's been no big LNG disasters. In ports nowadays, you'll find that security is a big issue, particularly from the point of view of anyone trying to carry out an act, terrorism or damage or destroy a vessel. And if you wanted to pick a big target, then you choose an oil tanker or a gas carrier. So not only are we do have to look after the safety aspects and the operational safety, we also have to make sure security-wise that no one unauthorised gets onto the terminal or onto the vessel that can interrupt cargo or cause any damage or anything that would lead to a cell loss of containment or an explosion. That's the world we live in. Any other questions? Some pictures of the insides of the tanks, the LNG cargo tanks, and that's a compressor. So these vanes are variable, so that alters the flow rate of the gas that's passing through it. They're constructing the tank made of special stainless steel. The coatings. They're building the tank sections, putting in insulation. See, it's wooden. Wood's a good insulator. So this will be filled with other insulating materials as well. So they're actually cutting all the pieces of shape. You can see once you're inside the tank. I mean, this is what a tank actually looks like even after it's had cargo in it. When the cargo's all evacuated out, it is absolutely spotlessly clean, you know, to enter, and then see the tank stasis. What was that? Okay guys, what's next up in your program? Chip stability. I think that's just about it. That's a wee bit early, isn't it? No more questions? Tired? Been a long day?
Yeah, you have to come every. Otherwise, they will skip the class. I will skip the class. Yeah. Because of the recording. Because of the recording. He was very angry.
Thank you, everybody.